ಫಿಸಿಕ್ಸ್ ಸಿ.ಇ.ಟಿ ವಿಷಯಕ್ಕೆ ಸಂಬಂಧಪಟ್ಟಂತೆ ನಾನು ಇಂದು ವೇವ್ಸ್ ಮತ್ತು ಸೌಂಡ್ ಈ ರೀತಿಯಿಂದ ಡಿಸ್ಕಸ್ ಮಾಡಲಿದ್ದೇನೆ. ಮೊದಲಿಗೆ ಸಿನಾಪ್ಸಿಸ್ ನೋಡುವ. Restoring force on the particle executing a system is given by F equal to minus ky. For a particle to execute a system, force is compulsory, that is known as restoring force. It is equal to minus ky, that k is force constant and y is the displacement of the particle from the mean position. Then displacement of the particle executing a system is represented by the equation y equal to a sin omega t, where a is the amplitude of the particle, it is the maximum displacement from the mean position, and omega t is the phase of the particle, where omega is the angular frequency of the particle, which is expressed in radians per second. Next, velocity of the particle is given by v equal to a omega cos omega t, which is obtained by differentiating the equation y equal to a sin omega t. It can also be expressed as omega into root of a square minus y square. Velocity amplitude or maximum velocity of the particle is Vmax equal to a omega. Next, the particle acceleration is equal to a into a equal to minus a omega square sin omega t is equal to minus omega square y. Maximum acceleration of the particle is a max equal to a omega square. Velocity of the particle is 0 at extreme position and maximum at the mean position. The particle undergoing simple harmonic motion possesses maximum velocity at the mean position. Remember this, it's very important. And acceleration of the particle executing a system is 0 at the mean position. Means there is no acceleration of the particle at the mean position, and maximum acceleration is at the extreme position. Then energy regarding the particle executing a system. First one, the kinetic energy, which is equal to half mv square. Substituting the value of v as velocity, we get half m omega square a square minus y square. The maximum kinetic energy is at mean position and the kinetic energy at extreme position is 0, and the potential energy of the particle is u equal to half m omega square y square, and the total energy summing up these two expressions we get half m omega square a square, and the total energy of the particle is always constant, which is independent of the variable term, say displacement, and it is a constant in case of undamped oscillation. Then coming to the system of particles executing a system. First one, loaded spring. When a load is attached to the spring and given a small oscillation, the time period of oscillation of the particle, that is the load, t equal to 2 pi into root of m by k, where m is the mass attached to the spring and k is the spring constant of the spring. Next, the time period of the oscillation of simple pendulum is t equal to 2 pi into root of L by G, where L is the length of the pendulum, which is the length from point of suspension to the center of gravity of the bob, and G is acceleration due to gravity at that place. Here, based on this, problems can be asked, that is depending upon the length or acceleration due to gravity. Whenever the length of the pendulum increases, the time period of the simple pendulum increases, that is it slows down, and whenever the acceleration due to gravity changes, that is when we go from one place to another place, acceleration due to gravity changes, the time period also changes. Suppose if we go from equator to the pole, acceleration due to gravity increases and the time period of that pendulum decreases, provided the length must be taken same. Similarly, when we go from earth to moon, the acceleration due to gravity decreases nearly to 1/6 of the g value, so that the time period increases, that is the pendulum oscillates slowly on the surface of moon. Next, coming to the topic wave. The phase difference between the two particles on the wave is equal to 2 pi by lambda in times the path difference, where 2 pi by lambda is known as the propagation constant and lambda is the wavelength of the wave, and wave velocity is equal to v. equal to lambda upon t, that is the wavelength upon time period of the wave. Using the value of 1 by t equal to f frequency can be written as f lambda, or the wave velocity is also expressed as omega upon k. K equal to 2 pi by lambda is called propagation constant or angular wave number, which is expressed in radian per meter. When a wave travels from one medium to another medium, its frequency remains same, but the velocity and wavelength change. Then different forms of progressive wave equation. The first equation, y equal to a sin omega times t minus x by v. It can also be written as a sin omega t minus kf. Using omega equal to 2 pi by t or k equal to 2 pi by lambda and v equal to omega upon k, you can write the different forms of equations. That is y equal to a sin 2 pi times t by t minus x by lambda, or y equal to a sin 2 pi by lambda vt minus x equal to a sin k times vt minus x, because 2 pi by lambda is k. And it is convenient or easy to remember the equation a sin omega t minus k, and remaining all other forms can be obtained by substituting omega, k and v value. Next, coming to the velocity of sound, that is first formula is given by Newton. Velocity of sound of a longitudinal wave proposed by Newton, v equal to root of e by rho, where e is known as modulus of elasticity of the medium and rho is the density of the medium. For solid, the modulus of elasticity is equal to y, that is equal to Young's modulus, and for fluids we said that modulus of elasticity E equal to d, that is bulk modulus. For gases, the bulk modulus is equal to pressure P. Hence, Newton said that velocity of sound in gas V is equal to root of P by rho, where P is the pressure. And Laplace has corrected that formula because the formula given by Newton found to be incorrect when checked with the experimental values, and he considered the propagation of sound is adiabatic process. So Laplace has corrected the bulk modulus, which is equal to gamma p, it's not just t. And the velocity of sound is given by the expression, or can be written as v equal to square root of gamma p by rho. It's equal to gamma RT by m, where gamma is the ratio of specific heat and R is the universal gas constant, T is the temperature expressed in Kelvin, and m is the molecular weight of the gas. Next, effect of temperature on the velocity of sound. If the temperature of the medium changes, velocity of sound also changes. And how it changes? As we have seen in the previous slide, V is proportional to square root of absolute temperature T. We can also write at two different temperatures the ratio of velocities as V2 by V1 is equal to square root of T2 by T1, where T2 and T1, capital T1 and capital T2 are expressed in Kelvin, or we can also express in degree Celsius, that is T2 small t2 in expressed in degree Celsius and small t1 expressed in degree Celsius, adding 273 as shown in here. Next, velocity of sound at t degree Celsius is given by the expression Vt is nearly equal to V0 plus 0.61 t. That is, for every rise in temperature of 1 degree Celsius, the velocity of sound raises by 0.61 meter per second. That is, the velocity of sound at any temperature is velocity at 0 degree Celsius plus 0.61 times that temperature, and the T is expressed in degree Celsius. For small values of temperature, we can just adding 0.61 times that temperature value to the 0 degree Celsius value of velocity, we can get the velocity of sound. Next, some facts about velocities of sound. That is, among the gases, velocity of sound is highest in hydrogen, and it is because the molecular weight of hydrogen is the least among the gases, and sound travels faster in the moist air than in dry air. It is because the density of the moist air is much lesser than density of dry air, and there is no effect of frequency on the speed of sound. Next, velocity of sound in different media are compared here. That is, sound travels fastest in solids and slowest in the gases. Next, coming to the intensity. So intensity of a mechanical wave is represented by the equation I equal to 2 pi square f square a square rho v. So here, when the amplitude is doubled, what happens to the intensity, or frequency is doubled, what happens to the intensity? Such questions can be asked. Next, intensity level of that sound. Intensity level is expressed in bell as logarithmic ratio of I by I naught. That is, base is considered to be 10 here. I is the intensity of that wave in the medium, and I naught is the standard value of intensity, whose value is equal to 10 raised to minus 12 watt per meter square. And the same is expressed in decibels. That is, IL equal to 10 times log of I by I naught. That is, dB is the symbol for decibel. And frequency range of audible sound is 20 Hz to 20 kHz. That is, the frequency between 20 Hz and 20 kHz are audible. Human being can detect only these frequencies, but some animals detect frequencies or sound can be heard to those animals beyond these frequencies also. Next, audible range of intensity. That is, minimum intensity what we can detect is 10 to minus 12 watt per meter square. It's considered standard intensity. And maximum intensity is 1 watt per meter square, which we can tolerate. Next, coming to the topic beat. When two waves of slightly different frequencies superpose, there is a slight waxing and waning of sound. There is sudden increase and decrease in the pitch of the sound heard. The number of beats heard, we call them as beats, and the number of beats heard is equal to the difference between the two superposing waves, and the time period between two successive maxima or successive minima is the reciprocal of beat frequency. That is 1 upon frequency, beat frequency. Next, the Doppler effect. When a source and sound moves, or whenever there is a relative motion between the source and the sound, the apparent frequency, that is the frequency as heard by the observer, is different from the actual frequency. So coming to a general case here, that is, when the source is moving towards the observer, source emits sound of frequency F and it is moving with a velocity Vs, and the sound which is emitted by source moves with a velocity V, and observer is also moving away from the source with a velocity V naught. Then the apparent frequency, that is frequency as heard by the observer, listener, is equal to F times V minus V0 upon V minus Vs. That is VO, we write, that is velocity of the observer, and Vs is the velocity of the source, and V is the velocity of the sound. So look at the diagram, that is all the three are in the same direction, then the formula is this. Then different cases, that is observer moving towards the source, then in case of V0 we have to substitute VO, we have to substitute minus VO, so that the formula becomes V plus VO upon V minus Vs. And whenever stationary observer or source is stationary, we have to take the values of velocities as 0, and always consider that the direction of sound, that is velocity from source to the observer. Then the relative directions of source and observer to be considered. Next, Doppler effect is asymmetric in sound and it is symmetric in light. Stationary waves. When two waves, one is traveling along positive x-axis denoted by the equation y1 equal to a sin omega t minus kx, and the other one y2 equal to a sin omega t plus kx, moving along negative x-axis. That is, these two waves are moving in the opposite direction, superposed to give stationary waves. The wave pattern found to be stationary, and the resultant displacement of the waveform is equal to, adding up these two equations, we get 2a cos kx into sin omega t, where 2a cos kx term represents the resultant amplitude. That means that resultant amplitude is variable. It's not a constant. It is depends on the value of x. That is, at different positions the amplitudes are different. Next, the distance between two consecutive notes or two consecutive antinodes is equal to lambda by 2. that is the distance from one node to next neighboring node, or distance from one antinode to another antinode, neighboring antinode, is lambda by 2. Similarly, the distance between one node and its nearby antinode is equal to lambda by 4. And the velocity of transverse wave along stretched string is given by the expression V equal to square root of T by M, where T is the tension acting along the string of thread and M is the mass per unit length of the thread, which is also called as linear density, that is the mass of the string upon its length. So that ratio is known as linear density, or M, denoted by symbol M. Next, the stretched string vibrates in different modes. The fundamental mode, or say first mode, is the frequency of the mode is known as fundamental frequency, which is given by the expression F1 equal to 1 by 2L into square root of T by M. And the different modes of vibrations have the frequencies, higher frequencies, where in case of stretched string, the overtones, different frequencies are in the ratio 1:2:3, etc. It means all the harmonics are present in the stretched string. And in case of closed pipe, you have seen the resonance column experiment. In case of closed pipe, the fundamental frequency is given by the expression F1 equal to V upon 4L, where V is the velocity of sound and L is the resonating air column, length of the resonating air column. Next, the different frequencies are in the ratio 1:3:5, etc. That is, only the odd harmonics are present in the mode of vibration of closed pipe. In case of open pipe, which is the pipe open at both the ends, the fundamental frequency is given by F1 equal to V by 2L. So we consider a term end correction, that is, the antinode is formed a little outside the open end of the pipe, whether it is closed or open. Antinode is a little outside the end, open end, so that antinode, the distance between the antinode and the actual end of the pipe, E, is equal to 0.3 D, where D is the diameter of the pipe. And when applying end correction to the closed pipe, the fundamental frequency can be written as F1 equal to V upon 4 times L plus E. Instead of length, we consider here L plus E, because in case of closed pipe, only one end is open, so E to be added. Whereas in case of open pipe, both the ends are open, so end correction to apply to both the ends, so it is L plus 2E to be considered. Coming to the last topic, acoustics of building. So important formula, that is Sabinet's formula for the reverberation time, is given by T equal to 0.165 V upon summation AS, where V is the volume of the hall and summation AS is known as absorption power of the all the surfaces, that is sum of the products of absorption coefficients of different surfaces and surface areas of different surfaces. And optimum reverberation time for speech, it is 0.5 second to 1 second, and for music it is 1 second to 2 seconds. And absorption coefficient of open window is equal to 1, that is the ratio of the amount of intensity of light absorbed, amount of intensity of sound absorbed to the amount of intensity of sound incident on the open window, which absorbs all the intensity incident on it, so therefore absorption coefficient of open window is 1. Next, coming to the problem section, I'll discuss some of the problems, important problems. First one question: in simple harmonic motion, the particle is always accelerated, always retarded, alternatively accelerated and retarded, neither accelerated nor retarded. So in case of simple harmonic motion, whenever the particle moves from extreme position to mean position, its velocity changes from 0 to maximum value, so that its acceleration is positive. We say that it is accelerated. And whenever the particle goes away from the mean position towards the extreme position, its velocity decreases from maximum value to 0, so it is retarded. So therefore, when the particle goes from extreme position to mean position, it is considered as accelerated, and whenever the particle goes from mean position to extreme position, it is considered to be retarded. Therefore, the option number 3 is the correct answer. Question number 2. A hollow ball is filled with water and then used as a bob of simple pendulum. If the water drains out of a small hole at the bottom, then the time period. Option 1 decreases, 2 increases, 3 remains same, 4 first increases, then decreases, and ultimately acquires the initial value. Here we know that mass of pendulum is not going to occur. So in case of ball with water, the length is from the point of suspension to the center of the ball, because it is just similar to solid ball, and say length is L. Next, when the water slowly drains out of the ball, only lower part there will be water, or the center of gravity of the system, that is ball and water, slowly shifted downwards, so that the length of the pendulum increases. So whenever the length of the pendulum increases, its time period increases, as time period is directly proportional to the rate of the length. And that is when all the water drains out or leaks out of the ball, now only ball is there, so the center of gravity of the empty ball is geometric center. So again the length, final length is equal to initial length. So therefore the time period in the end and in the beginning are same, and in between it increases as the length increases and it decreases as the length decreases. So therefore the option number 4 is correct. A particle executing SHM has a potential energy CE, kinetic energy KE, and total energy CE are measured as a function of displacement x. Which of the following statements is true? Options are: first one, potential energy is maximum when x equal to 0, kinetic energy is maximum when x equal to 0, total energy is maximum when x equal to 0, and kinetic energy is maximum when x is maximum. It's a knowledge based question. That is, when the particle executing SHM, which is at mean position, the displacement is 0, x equal to 0. When the displacement is 0, the kinetic energy is maximum. We know that velocity is maximum, and kinetic energy also maximum. Hence, at kinetic energy is maximum at the mean position. Therefore, the option number 2 is the correct answer. That is, kinetic energy is maximum when x equal to 0, that is at the mean position. And the extreme positions, kinetic energy will be 0 or considered as minimum. And at the mean positions, potential energy is considered to be 0. Next, question 4. Two simple harmonic waves are represented by the equation y1 equal to 5 sine of 2 pi t plus pi by 4, and the second wave y2 equal to 5 sine of 2 pi t plus root 3 cos 2 pi t. The ratio of their amplitude is: first option 1:1, second option 2:1, third option 3:1, and the fourth option 1:2. Here, just by observing, you may think that the ratio of amplitude is 5:5, that is 1:1. But it is wrong, because the second equation y2 is sum of two functions, sine and cosine. So we need to express that function as single function. So to write that single function, that is in terms of sine or cosine, we have to use mathematics. That is, take half, take 2 outside, so that we can write half here and root by 2 here, as we studied in general solution. So the amplitude of the second wave becomes 10, and here within the bracket we have sine of 2 pi t plus pi by 3, and the required ratio, that is ratio of amplitudes, becomes 5:10, that is 1/2 or 1:2 ratio is the correct answer, which is option number 4. So here, whenever these two waves suppose superpose, the resultant amplitudes also can be asked, which can be found by using the formula r equal to square root of a square plus b square plus 2ab cos phi, where phi is the phase difference between the two waves. Here, phase difference between the two waves, between this and this, we have to find out, and a is 5 and b is 10. And similarly, further ratio of intensities also can be asked. That is ratio of I1 is to I2, that is equal to square of the amplitude, ratio of squares of amplitude, that is pi square upon 10 square, or it is 1:4. Next, the question number 5. Both light and sound waves, option 1, travel in vacuum. 2, can be polarized. 3, carry energy and momentum. And fourth option are electromagnetic in nature. The first option, travel in vacuum. It is not applicable to sound, as sound waves are mechanical in nature, which require material medium. So in the free space or in vacuum, sound waves cannot propagate. Only light waves can propagate in vacuum. So first option is not correct. And can be polarized, again, which is applicable only to light. Sound waves are longitudinal, light waves are transverse. Only transverse waves can be polarized. So light waves can be polarized, but sound waves cannot be polarized as they are longitudinal. So option 2 also wrong. And carry energy and